All right, Calc AB, day 2 notes, conquering infinity. But really, when we think of infinity in calculus, we're going to be thinking of breaking things up infinitely. So we're going to be thinking of lots of things, small things. So there's two key issues in calculus. That's it. Just these two issues, derivatives and integrals. We're going to cover both of these throughout the whole year. And so I'm just kind of giving you these ideas to kind of motivate why we want to think about limits and different things like that. Now, the derivative is like finding the slope of the line of a curve. Now, this slope is changing. And if you wanted to find the slope here, now you guys have found lots of slopes, but of straight lines, which require 2 points. So before calculus, we couldn't do this because you only have 1 point. We could only find the slope between 2 points, and we don't have 2 points. We have 1 point. So how do we do this? Well, what we could do is we could take another point on the curve and connect it with what we call a secant line. So the first line, the slope is a tangent line. A line that intersects the curve more than once is called a secant line. You say, well, that's kind of a rough idea of the slope. Or you could take one over here and say, well, that's a rough idea for this slope. This is the one we're trying to find. But the key idea is if we move these closer to each other, the estimate gets better and better and better. And this is actually how our calculators do it. My calculators use a GAF 0.001 to find derivatives. It doesn't do it exactly. It's an estimation technique. Now, this is where the idea of limits come in. We're going to take these points so that they're infinitely close to each other. We're going to take the space between them to become infinitely small. Okay? Integrals. One idea is that if you're finding the integral between these 2 points, that you're trying to find the area under the curve, between the curve and the x-axis. Right? Now, the approach we're going to take in calculus is that we're going to slice this up into really thin bars. And we might even treat them like rectangles, even though they're technically not. But we're going to just slice it into lots and lots and lots and lots of skinny slices. Okay? So we're going to break it up into infinite slices. And these slices are infinitely thin. They're very thin. Okay? And then we're going to add them all up to get the area. And that's where I was talking the other day about integrals being accumulators, adding things up. So, anyways, that's just kind of an intro into those two big ideas that we're not going to really get heavily into for a while. You can stay, but you can never leave. Zeno's paradox. So I was talking about this in the warm-up. You could go halfway to the door of the classroom and then go halfway of what's left. And according to Zeno, you can't get there. Can't ever get there. Can't get out. Okay? Just kind of I think I could, yeah, I agree. If I have to go half of what's left, then I'm never going to be able to go all of what's left. So this goes into this repeating decimal idea. I showed you guys an example in the warm-up. So we're going to do some of these on today's assignment. So what we're going to do, now some of you guys I think already know that these repeating decimals can be written just nicely as a fraction. But I'm going to show you some that you won't just recognize. So how can we find it? So one idea, and this is just to kind of set it up, is that we could think of this as 3/10 plus 3/100 plus 3/1000 and so on, right? So it's this kind of infinite idea. In fact, in AP Calculus BC, this is called an infinite series, which I don't know, you actually can study those in algebra, but we're going to do a bunch of work with them. Now, here's the trick. However many numbers are repeating in this, let's multiply by 10 to that power. So 10 times n, we're going to multiply both sides by 10. This thing become 3 plus 3/10 plus 3/100 plus 3/1000 would be the next term, which used to be 10,000s, and on and on and on. And then we're going to subtract the original number, but we're going to line it up out of convenience. So you got to distribute the subtraction. I'm going to line up the terms that match up to those terms. And there's going to be an infinite number of terms, and they're all going to cancel each out, all the rest of them. And what you're left with is 9n equals 3, and n equals 3/9. So n equals 1/3. Now, I did this on purpose on an easy one, just so you felt confident in it, but we're going to do it on some more hard ones. I don't think you guys would recognize what these would be as fractions, and these aren't that bad. So here's the trick. I'm going to multiply by 10 to a power. And in general, it's whatever is necessary to have the original repeating decimal left over. So I'll show you how this works, and then you guys get to practice on your homework. Okay, so this first one, we're going to say n equals, and I'm going to actually show you doing the wrong thing first. So so far I've shown you this 10 thing. If we multiply both sides by 10, on this one it'd be 4.24 repeating that way. Like, you don't write the repeating over the part in front of the decimal, but it's 4242. So we could say 24, or even 242 if you want, and get rid of it here. The problem is that when you go to subtract n from it, the repeating part here won't nicely cancel out with that repeating part. So that doesn't work, right? We need a 0.42 repeating right here to nicely cancel with that. So in this case, if we multiply by 100 on both sides, we get 42.42 repeating, right? And then when we go to subtract n to get rid of the repeating part, it lines up really nice, and they just cancel each other out, and I get 99n equals 42. I divide both sides by 99, and I get n equals, I could reduce this, take a 3 out, 14/33. Okay, so the trick is to multiply by 10 to a power, what is necessary, okay? And so here there were 2 repeating decimals, so we had to multiply by 10 to the second. This has 3 repeating decimals, so we need to multiply by 10 to the third. So I'm going to say n equals, I'm going to multiply both sides by 1,000. And what that does is it gets it to a point where that repeating decimal is going to line up nicely when you go to subtract it to get rid of it. It's got to line up nice. So we get 999n equals 123. And we divide both sides by 999. And it's possible to reduce this. You could divide a 3 out of this. It would be 41 over 333. So now the next one's kind of tricky. You might be tempted to multiply both sides by 1,000, but there's only 2 repeating numbers. So we're going to multiply by 10 to the second. So we're going to do n equals, We do 100 in, and it's going to move the decimal place over 1, 2 spots when you multiply by 100. And then the repeating part, it's 2, 3. You could write it like that, and it is going to go 3, 2, 3, 2, 3, 2. But when you go to subtract it, it doesn't line up right. Now, that doesn't mean we didn't multiply by the right number. It just means that maybe we should actually keep the 3 next and instead call it 3, 2, 3, 2, 3, 2, 3. It's the same number. We're just kind of thinking of the repeating part in a different way so that these cancel each other out. So we get 99 in. Now, something interesting happens here. The decimal doesn't go away. The repeating part goes away. We still have a decimal. And in math, we don't like to have fractions with decimals in them, or fractions with fractions in them usually. So the solution is to move the decimal over by multiplying the top and bottom by 10, and we get 122 over 990. We could reduce that by dividing 2 out of both of those, 61 over 495. Next one, we're going to multiply both sides by 10. Now, you can multiply by bigger powers of 10 than what I'm doing here, and it'll work. The problem is you get bigger numbers than you need to. So we're trying to keep everything as nice and simple as possible. So it's going to be 4.5. Now I'm going to subtract and I'm going to subtract 0.45, and I want to line up the decimals. And here, this is where repeating is. Well, let's just put a 5 here and say that's the repeating part. Okay, that's the same thing. So multiply top and bottom by 10. There you go. So next one, multiply both sides by 10. And we get 9. And now this one's the interesting one, 0.999. Look what it turns out to be. What? 0.9 repeating is the same as 1? That'll blow your mind. But there you go. I mean, mathematically, we just proved it. So, kind of interesting. On the back is just a little bit of math history. Not necessarily required for the homework, but just some ideas to think about. So some just counting like 1, 2, 3. The first evidence that people found of that was called the Ashango bone, and it was they estimated 20,000 years old. First evidence of humans counting. Now the Indians and Mayans started using whole numbers, including 0. Okay, and that's sort of the basis of our decimal system, because you can write any number with 10 symbols, and the idea is that we have 10 fingers. I mean, we often use our fingers to do simple counting. Now, integers, now these are whole numbers, okay? And that includes 0. Integers include the negatives, -3, -2, -1, 0, 1, 2. And using negative numbers was definitely a leap in our mathematical abilities. Before we actually used negative symbols, they might use, before negative symbols, they might use a color like red. And that idea of banks, you're in the red, in the black, you owe money if it's red. Black Friday, companies are now in the black, they're making profits. Rational numbers can be written as P over Q, a ratio of integers, and Q cannot be 0. Decimals, if they're terminating, that means they end, then yes, they can be written as a rational number. If they're repeating, non-terminating, and they're repeating a pattern, then they can also be written as a fraction. We call those rational numbers. Sort of a geometric way of showing how, to get a fraction of something else is that you could take a line and you say, well, I want 3/5 of this line. And let's say you don't have a ruler. So I want 3/5 of this line. How would you do that? Well, what you could do is you could take something and draw a straight line off of it. Okay. And then what we're going to do is we're going to take this line and use maybe a compass and break it up with even as many chunks as the denominator is. So then we could take 3 of these, and what we need to do is we need to connect the ends of these with a line, and then we can take the third one and construct a parallel line to this line. And using a compass, you can do that. You can copy angles. As long as this is parallel, then what that does is each of these lines, in fact, if you were to draw other parallel lines and they would have equal angles, they would all cut this into fifths. But this right here would be 3/5 of that line. Now, irrational numbers are non-terminating, non-repeating decimals. And there's some famous ones like e and pi and square root of 2 and so forth. And you can't do this trick that we did for 3/5, you can't do with rational numbers. We're going to be dealing with real number system and complex number system, even though that in AP Calculus A, B, and BC, College Board's content does not include any imaginary or complex numbers. Interval notation. This is something that's probably going to be kind of new for some of you guys. Usually last year, if I were to ask you to write an answer that represents this, you'd say, oh, well, that's 2 is greater than or equal to x and less than 5. That would be interval. This would be that would be the notation you used last year. And we might use that. We'll use that sometimes, but there's a notation that's very common on the AP test. So you need to become very good at. It's called interval notation. And it says, okay, well, let's just use one side, comma, the other side. And then we'll use a bracket or parenthesis to decide whether to include it or not. So included is bracket. Excluded, open dot, not equal to is parenthesis. So bracket includes the endpoint. And that would be, less than or equal to, or greater than or equal to, in parentheses, excludes the endpoint. So that would be just greater than or less than. So this right here, last year, you might say x is less than 3, right? This year, so I'm going to ask you to do this on your homework because I want to get used to this. This year, we would say negative infinity to 3. And then we always put parentheses on infinity because bracket would indicate that you actually included infinity and that you're able to get or have infinity. Infinity goes on forever. So on today's homework, just to give you a sneak peek, there's some variety of problems on the front. Are the following integers rational or irrational? Convert these repeating decimals to rational expressions. So that's what I showed you guys how to do in the notes. Some different things about pi. And then on the back, something I didn't really talk about, but I think you guys can do. This is some just review of solving inequalities. Now, if they're linear inequalities, that's pretty easy. You just say, all right, well, let's get x by itself. Okay, and that's the answer. Now, in interval form, that would be negative infinity to 4, parentheses, right? You could, write your answers both ways. Write them the way that you would before, and then write them the new way. But this right here, this is a quadratic inequality. And this one, trying to get x by itself doesn't really work so well. In fact, on number 24, I would say this is similar. Some people would be tempted on 24 to say, well, let's take the square root of both sides. X is greater than plus or minus 3. And that's not really the answer. So what I would advise anytime you're doing any kind of more than linear, more than first degree, more than power of 1 on the x, move everything to one side equal to 0. Okay? And then try and factor it. X plus 3, x minus 3. Let's try and factor it. Okay? So this one right here, you want to try and factor it. You want to find the things that make it 0, because those are going to be points where things change whether they work or don't work. So two numbers that multiply together get positive 8, add together get negative 6, minus 2, minus 4. So x equals 2 and x equals 4, right? In this case, x equals negative 3 and x equals positive 3. Now, in your Algebra 2 classes, Algebra 1 classes, your teachers may have said, okay, well, let's put these on a number line. They're going to be open dots because it's less than. These ones would be solid dots, which I would recommend doing. And then they might tell you, test each region, test a point here. Because what's going to happen is the whole chunk's going to work or not work. So you could test x equals 5, and you test in here, is that less than 0? Yes. And then you could test a value here, x equals 3. Is that going to be less than 0? I'm sorry, when you put 5 in, it's actually false. When you test 3, it works. And then when you test, say 1, it's going to end up being negative times positive, which is going to be false. And so then this is where your answer is. And this is your final answer. Now, the way you would write this before is you write like that. But the way we're going to start writing it now, interval notation, is like this. Right? So you'd say false, true, false, and then that's how you'd find it. So go ahead and use that method, or this is a way I like to always show my students. I would say, okay, let's do this. Let's find these points, and then let's imagine this is a graph, and this is where the y value is. Okay? And I'd say, well, this is the graph of parabola that's opening up, right? Now it's going to be dashed because it's or equals to. And then I'd say, well, should I shade up or shade down? This is where the y is. Y is greater than that. I'm going to shade up. And then I'm going to say, okay, well, really I'm just concerned with where y equals 0. And then that's going to be the line right there. And you get the same answer. That's what I like to do. But that gets a little harder in some examples. But anyways, try to do these however you learned before. You could use either of these approaches. Try and write your answers in interval notation after writing them the way you might normally write them. Okay? And then try all the homework, check your answers online, and we'll go over some questions tomorrow in class.